Magnetars are a type of neutron star. They all possess extremely strong magnetic fields. Through their decay, they can continuously release high-energy electromagnetic radiation, mainly X-rays and gamma rays. The magnetar theory was first proposed by scientists Robert Duncan and Christopher Thomson in 1992. In the following years, this hypothesis was widely accepted to explain the source of repeated bursts of soft gamma rays. Observable celestial bodies such as soft gamma repeater and anomalous X-ray pulsar. When a large star bursts through a supernova, it will collapse into a neutron star, and its magnetic field will rapidly increase. According to the calculation results of scientists Duncan and Thomson, its intensity is about 100 million Tesla, 108 Tesla, and in some cases it can reach 100 billion Tesla, 1011 T, 1015 Gauss. These extremely strong magnetic field neutron stars, it is called a magnetar. The intensity of the natural geomagnetic field on the Earth's surface is about 3.5 times 10^15 near the equator and about 7 times 10^15 near the poles. A supernova may lose about 10% of its mass during an explosion. A star with a mass 10 to 30 times that of the Sun needs to release more mass to avoid collapsing into a black hole. 80% of itself. It is estimated that in every 10 or so supernova explosions, one will become a magnetar instead of a normal neutron star or pulsar. Before they evolve into supernovae, they need to have a strong magnetic field and higher rotation speed in order to have a chance to evolve into magnetars. Some people believe that the magnetic field of a magnetar may be generated by convection through the hot core material in the first 10 seconds after the birth of a neutron star. The situation is like an engine. If the convection has a higher rotation speed, period of about 10 milliseconds, at the same time during the occurrence of convection, the current generated by it is enough to spread throughout the entire celestial body, and it is enough to turn its rotation energy into its magnetic field. On the contrary, if the rotation speed of the celestial body is slow, the current generated by the convection of its inner core material is not enough to spread throughout the celestial body and only flows in a local area. The outer layer of a magnetar contains plasma and iron-based heavy elements. During the period of tension, celestial bodies will have starquake, which can cause celestial bodies to release powerful energy, including X-rays. Astronomers refer to these celestial bodies as soft gamma-ray recurrence sources. If a magnetar is regarded as a recurring source of soft gamma rays, their lifespan is quite short. A star shock releases a large amount of matter and energy. The matter is trapped in its own strong magnetic field and evaporates within a few minutes. In addition, other matter that can be released in the form of radiation has its kinetic energy derived from the angular momentum of the celestial body, which slows down the rotation speed of the magnetar, and it decreases faster than other neutron stars. The slower rotation speed will weaken its strong magnetic field, and the magnetar's star shock ceases after about 10,000 years, during which X-rays will still be emitted, which astronomers call irregular X-ray pulsars. After about 10,000 years, its activities have almost ceased. Star shock is a kind of instantaneous large-scale destruction, some of which are directly recorded by people, such as SGR 18620 on December 27, 2004. With the increasing accuracy of astronomical telescopes, it is expected that people will be able to record more in the future. Phenomenon. Last year, an X-ray burst allowed scientists to discover an ultra-young magnetar, at the time, that was about 500 years old. For astronomers, it was almost as exciting as seeing a newly formed embryo. Recently, Australia's Ozgraph agency conducted a follow-up study on this magnetar and pointed out that it had a completely different form of activity from other magnetars. It sent out the radio waves of the magnetar all at once, and then sent out the radio wave pulses of the pulsar all at once. Magnetars are very rare neutron stars. The magnetic field is as high as 100 million Tesla, 108 T, and in some cases it can even reach 100 billion Tesla, 1011 T. This super-strong magnetic field can be half the distance between the Earth and the Moon. Demagnetize your bank credit card. Magnetars continuously emit high-energy electromagnetic radiation during the decay process, mainly X-rays and gamma rays, and can also generate radio pulses through a completely different process from other celestial bodies. Astronomers have discovered about 3,000 neutron stars so far. However, there are only 31 magnetars, most of which were detected by X-ray telescopes after experiencing high-energy bursts. However, there are very few magnetars that emit radio pulses similar to pulsars. On March 12, 2020, scientists used NASA's Neil Gehrels Swift Observatory to discover the youngest neutron star Swift J1818.01607, abbreviated as J1818, in a bright X-ray burst, and follow-up observations and corrections have confirmed that it is the 31st known magnetar, 21,000 light-years away from the Earth, and its age is about 500 years old. J1818 is also faster than other magnetars, rotating once every 1.4 seconds, and it is the few magnetars with pulsar characteristics. In order to track the changes in J1818 over time, the Australian Gravity Wave Research Agency OzGrav team used the Parkes Observatory's radio telescope to observe it 8 times, and found that J1818 seems to have gone through a split period. A pulsar like radio, the radio wave pulse suddenly switched to the typical bright radio wave form of a magnetar, and even the two were mixed for a while, as if J1818 was uncertain whether it was a pulsar or a magnetar. However, the above phenomenon is very short-lived, and the last observation indicated that J1818 has been permanently shaped as a magnetar. The team's observations showed that the magnetic axis of J1818, like a pulsar, is not aligned with the axis of rotation. Its radio signal comes from the magnetic poles below the equator in the southern hemisphere, while other magnetars usually tend to have a magnetic axis aligned with the axis of rotation. Fortunately, this kind of misalignment, the shape is also quite stable in most observations, indicating that the radio wave pulse changes are caused by the different heights emitted above the surface of the neutron star. Although researchers have not been able to explain clearly how J1818 emits different forms of radio waves, it may represent a form of stellar evolution that we have not yet understood. Maybe magnetars can evolve from pulsars over time? The new paper was published in the monthly bulletin of the Royal Astronomical Society, NAS.